Hello, Dr. M here. In this video, we're going to talk about electrophilic aromatic substitution. Part of it is aromatic halogenation. You're putting a halogen on the ring. The reagent you're using as a Lewis acid to activate the reaction is iron trichloride or iron tribromide, which is this species or that species. Okay, where the X is a halogen. So it's electrophilic aromatic substitution. We are substituting a hydrogen with a halogen, in this case X. The Lewis acid, the FeCl3 Lewis acid, just makes the halogen a strong electrophile. Again, remember, in electrophilic aromatic substitution, the benzene ring or the aromatic ring acts as a nucleophile. Okay, and the electrophile is generated in situ within the reaction. So take this X2 to be 2Br atoms. So one of the halogens will use its lone pair to attack the metal center. The rest of the halogens will not leave, they'll just stick on there. And then the species that's formed is gonna have one of the halogens that was used to attack having a plus formal charge, and the ion will have a negative formal charge. The species, the compound can break apart to form a halogen cation. So these species can be used in the mechanism as an electrophile, or this X plus can be used as an electrophile. Okay, so what's the mechanism for electrophilic aromatic substitution? Overall, the hydrogen on the ring of overall the hydrogen in the ring is going to be replaced by the halogen. So hydrogen switched to halogen, that's substitution. And you're taking the electrophile to be this species or its equivalent, which is X plus, according to what we've shown here. Okay, and we start by the ring attacking the halogen on the electrophile, and this part will leave. That's how you get this species over here, and we are saying is gonna go here where the hydrogen that's shown on the ring is sitting, and that means the plus charge will end up here next door. So you get this intermediate. After the bond opens up to grab a hydrogen, this carbon is left with one valent electron less, so it has to be a plus charge. And then the species that fall off is gonna use a bond to one of the halogens bonded to the ion to grab the hydrogen on the ring, and in turn give back the pi bond to the ring, so the ring becomes aromatic again. This intermediate rhenium ion intermediate here is not aromatic, and so that means it's less stable, so the ring rearomatizes to be more stable. So this step right here is called rearomatization. So this step right here is called rearomatization, because you're forming the aromatic ring. The ferric trichloride or tribromide is recycled from this step. That's why it's only used as a catalyst. Now this rhenium intermediate bearing a plus charge can generate more resonances. So if you withdraw it here, if you withdraw it here, if you push this pi bond towards the plus charge, you're going to leave a plus charge behind, you get this structure. If you move it again towards this plus charge, you're going to get a plus charge where the arrow is, you get the third structure. Overall, the plus sign is starting here and it's ending up there, so we can generate a resonance hybrid showing where the plus charge was and where it ended up. So that's a resonance hybrid structure if you're asked to draw. Let's look at worked examples. what are the major organic products to the following reactions. Now again, you have to realize this is electrophilic aromatic substitution, EAS, and this combination should just be able to give you Br+, which will substitute the hydrogen. So that's the product, that's the major organic product. HBr is just a byproduct. If you're doing chlorination, then you need the FeCl3 version with the Cl2. So the Br goes to the Br, the Cl goes to the Cl. This will give you a Cl plus electrophile, which is going to substitute the hydrogen to put a Cl on there. Okay. For question 3, you have a methyl just doing some cleaning up. Perfect. For question 3, you have a methyl bonded to the ring. It's actually an electron donating group. It's donating through bond by induction. So since it's an electron donating group, it should direct the incoming electrophile, ortho or para. This is the ortho position, and here where you have a hydrogen, that's the para position, which is complete opposite side. To refresh about directing groups, click the link below this video to know which groups are donating, which groups are withdrawing, which groups direct ortho para, which groups direct meta. Anyway, the electrophile C+ is electron donating group, so you're going to get either putting Cl ortho or para, but in this case, if you put a Cl here, is going to be crowded with the methyl group, so it will rather go para to give you the major product. Okay, so it's the para hydrogen, this hydrogen here, that's going to be substituted with a Cl because it's farther away from the methyl, avoiding sterics or crowding. For the next question, so question number 4, you have a ketone group. Across the carbonyl, you have electron, you have dipole-dipole moments going on because oxygen is more electronegative than carbon. So in turn, you're stealing electrons from the ring, and that's deactivating the ring. We started by saying the ring must be electron rich for it to do the reaction quickly. But anyway, the reaction is still gonna happen here, but it's going to put the electrophile on meta position. So the meta position is 1 carbon over. You skip 1 carbon from the group. That carbon is meta, and this is meta. So because the molecule is symmetrical right now, either of the meta position will be substituted with the Br+ from this reaction condition. So we put it on there. For this question, OH again has an atom with lone pairs on it, which can be donated to the ring, activating the ring, so we expect it to direct ortho para. OH is not a very big group, so most likely from this reaction mixture where you get your electrophile to be Br+, to try to halogenate the ring, the Br+ might go both ortho and para. So you could get these two products. Okay, if there's an excess, it could brominate the two orthos and the para. Okay, now because you are not told it's an excess, so probably the bromine, the electrophile will make it to go ortho, which is just a carbon next door to the group of interest, or opposite, which is the para position. So that's how we get these two products. Okay, all right, practice a lot, you get confidence. Thank you, see you soon, bye.